question 3 means. Just starts, come on. Oh, it's recording. Oh, and I'm not sharing the screen. Hello, world. That's better. Okay, so here we're going to play around again with the idea of groups. So we're taking our multiplication idea, applying it to division. So 17 divided by 4. So the recommended approach here is to make a little grid. We need to accumulate 17 things in the body here, and we're going to do it by working with the number 4 and then figure out what other number appears on the edge of the array there. And so there's 2 different ways to think about it. Somebody want to suggest how I should start dealing with the 17 things here? Find the answer. What should I write down?
Make a group of 4 first.
Make a group of 4, okay? So like vertically or horizontally?
I did mine vertically.
Okay, so 1, 2, 3, 4. So there's one group of 4, and then keep doing that, counting up to 17, right? Okay, so 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and then there's finally 17. So the question mark ought to be what here?
4.
Yeah. 1, 2, 3, 4. We got that partial group there. So what we end up with is that 17 is equal to 4 times 4 plus 1. So we just discovered this group here, and then we have our remainder there. And I think, let's see, I'm going to have to get to this problem on a different page. I think the question that we use to help solve this would look something like this. How many groups of 4 are in 17? Does that seem like a reasonable question that allows us to answer this? Yeah. And we found, well, there's 4 full groups with 1 left over. Would be our answer. Okay, so before we do another one written like this, what I'd like you to do is take whatever problem you did or my problem and write a story to go with it. What kind of scenario, what story problem would go with whatever numbers you wrote down or whatever numbers I wrote down? But just pick one set of numbers. Maybe it's 17 divided by 4. Maybe it's the first one you wrote down. But come up with a situation that we could use to deal with this instead of just drawing blocks or squares or circles or whatever we're drawing. Okay, so I wrote down 2 different story problems, and it's my belief that these story problems are fundamentally different. And so I want you to take a read at each of mine. So this is my story problem number 2. I got 17 burritos. I got 4 people in my family. I want to share them so that each person gets the same amount. How many does each person get? So that's one story problem to do by 17 divided by 4. And here's my other one. Gary made 17 enchiladas. 4 enchiladas will fit in a lunchbox. How many lunchboxes does he need? So I think these are different, not only because I'm talking about enchiladas and burritos, but I think they're physically different. Okay. So when we talk about multiplication, we talk about groups of. So we have a number of groups and then a number of things in each group. In this problem, is the 4 the number of groups or the number of things in each group? Yeah, here the 4 is the number of things in each group. So here I'm starting off with the assumption that I have 4 things in each group. Okay. On the other problem, is the 4 still the number of things in each group, or is it the number of groups? Yeah, here it's the number of groups, because I don't know how many each person gets yet, right? I haven't done that part. So here, there are 4 groups. So do you see that's my fundamental idea about how they're different? One says, hey, you got this many groups. How many goes in each group? The other one says, you got to give them away 4 at a time. How many groups does that make? So now think about your story problem. Does your story problem fit in the first category, where it's the number of things in each group, or does it fit in the second category? You know the number of groups to start with. So I'm kind of curious, how many people here, theirs was their number, their divisor, that's my 4 here is called the divisor, it's the number of groups. Okay, not sure on yours?
Yeah.
Or is your number the number of things in the group? You want to read it to us and we can help judge?
Sure, I don't know if it's right. I just said, Jeff has 21 pieces of candy.
Yep.
He wants to give 4 pieces each kid. How many kids can he give pieces to?
Yeah, so that's the first one. Okay, yeah, so that's interesting.
Okay.
Most people pick the second version where they had the number of groups out. And how many people were like giving stuff away or sharing stuff? Okay, so this is a pretty common thing. We look at division as sharing. When we share, we usually know how many people we're sharing with. Once in a while, though, it goes the other way. We don't know how many people we're going to share with yet, but we know once we share, each person's going to get 4, for example. That's a different scenario. It's physically different. Right? I'm doing it slightly backwards. So when I know the number of groups, that's called the partition model. Okay, so this scenario 2 right here is what's called the partition model for division. Partition model. And that's what they're referring to at the end, that last part in the second page of this activity. And again, think about it. I have 17 things, so I'm just going to draw this on a new page. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay. And what I want to do is I want to organize these things so they fit nicely in that situation. Okay, right? So think about partitions in a room. They break up the room. So that's what we're doing. We're saying, okay, 4, I want to have 4 places, partition the room so that happens, and then just start dropping these things in there. You know, one goes there, another one goes here, another goes there, another, oops, I missed. Another goes there. And then we just keep doing that, trying to get equal groups, divvying them up one at a time. Yes, there you go. I'm getting there. Glad I didn't pick a bigger number than 17. Oops, I missed. You go here. You go here. Is anyone going to complain yet? Everyone got the same amount, right? And we got 1 left over. So set partition model is what this picture looks like. Other model, I call this the groups in model. I'm going to put quotes around groups in. Because it asked the question, how many groups of 4 are in 17? I don't know the partition yet. So every model we use, basically it should lead us to ask a question, and then somehow we physically work through that question to get an answer. So that's what a model does. Why is the answer 4 with 1 left over? I can show you. Okay? So the picture that would go with this one would look more like this. Here's all my enchiladas. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17. Ooh, got it. Now this time I'm looking for groups of 4, right? So I really don't have to move them around so much as I have to just collect them. So here's a group of 4, and here's another group of 4, and there's another group of 4, and there's another group of 4. 4 groups. So the discovery here is that I got 4 groups. 1 left over. In the other problem, it was pretty different physically. Here, I knew how many groups. The discovery here is 4 in each group. So that's what we discovered there. It was like the same problem, but backwards.
What model was the other one?
The other one was called the set partition model. So this one here, or the first one? The first one, it's usually called the groups in model. Sometimes it's just called the set model. But the partition model is a set model too. So they're both set models. Often you'll see this one called the set model. So sometimes instead of groups in, it'll just say set. Otherwise, the other version of the set model is the partition model. And then they want us to describe the relationship between the partitioning model for division and multiplication. So in your own words, how is the work we did here related to multiplication? And you're going to have 5 examples, and the examples will have a problem, a picture, and then you can state the answer in a couple of ways. So here I stated the answer as a multiplication with an addition. The other way I can state it is the way they have it right here, where 15 divided by 4, in my case I'm doing 17 divided by 4, would be equal to 4, remainder 1. Now with kids, we'll tend to write it this way, and for years it's kind of sketchy exactly what a remainder is. It's just something left over, but a remainder actually is a fractional group. We'll talk about that next term. For now, it's just 1 left over. It's just a remainder. All right, let's see. Where is that? Now, the extension is the kind of tricky part. So if you have a calculator on you, get it out. Most calculators are on our phones these days. And I'm pretty sure my phone calculator cannot do integer division. So get your phone calculator out, or your computer calculator, whatever you happen to have nearby. I used to have an Android phone, and my Android calculator was identical to the Google calculator. So if I type 17 divided by 4, then it brings up the Google calculator here, which is what my Android phone calculator looks like. The iPhone calculators are a little bit different. So here it tells me it's 4.25. Now, when students first start doing division, they haven't done decimals yet, so that makes the calculator part tricky. Some classrooms will have special calculators that have a division, an integer division button, so the answer would pop out as 4 remainder 1 instead of 4.25. Okay, so that'll make more sense with the kinds of things the kids are used to writing on paper. But the 0.25, it's going to freak a lot of kids out. What's 0.2? I mean, they can say it. They can say 0.25, but they don't know it's 25 hundredths yet. Okay? They're doing division way before they get to that. So we got to figure out what to do here. So you guys, I'm taking you out of the role of elementary school kids with a special calculator. How would you, based on your calculator, figure out what the remainder is? So I'd just like you to think about that for a moment. Talk to your neighbor, try an idea out. But what we want to do is be able to take a regular kind of calculator, scientific or simpler, and be able to throw a division problem in it and be able to say, oh, here's the whole number part, here's the remainder part. So think about that, write something down, try it on your calculator, check it with your neighbor, and then we'll go over it together. And we're not going to do every one of those extension problems, we're just going to test a couple of them. So for example, we could use 64 divided by 3 as our first example. How would we use our calculator without having to draw a picture, like we were doing just a minute ago, to come out with the whole number and remainder part? Quiet. An idea to share with their neighbor? Yeah, you have an idea? You have an idea? You guys have an idea yet? No. Good. All right. Why don't you all talk there? One big group. Who wants to start? Talk to each other.
Okay, so I just divided 64 by 3, and it gave me a whole number of 21, and then 0.33. So I would multiply 3 by 21 because it was divided by that, which gives me 63, and would subtract 63 from 64, which gives you a remainder of 1. I don't know if that's how you would do it. But
okay, so that was good. So the calculator said that this was 21.33, and that just keeps going, right? Forever. That's a hard one to explain to kids, right? I have a hard time with it as an adult. So then he said, okay, well, the whole number part here, by the way, does anybody know the name of that 21, that whole number part? Starts with a Q.
Quotient.
Quotient, yeah, nice. This guy's here is the quotient. That's a G, it should be a Q. Quotient. How about this, what's the 64 called? Starts with a D.
Dividend.
Dividend. You guys are on a roll. Yeah, so we have dividend. And the 3
Divisor.
is the divisor. Divisor. There we go. And then obviously the other numbers are remainder, which we're seeking here, the whole number remainder. So yeah, so division and multiplication are related. So the next step would be to take 21 times 3, and that's going to give us 63, which is almost what we want. 64 minus 63 is equal to 1, so that must be the remainder. (21) remainder 1. Now, earlier I wrote my division as a multiplication problem and an addition. So we have this one way to write it here. Write it down as a multiplication and addition problem also. What does that look like? Give it a shot, and then I'll write mine down and compare notes. So there it is as a multiplication and addition problem. So there are calculators, just like they can be programmed to carry out division and give decimals, instead they could be programmed to spit out the remainder instead. Okay? Now how would you do this without a calculator? So I don't have a calculator nearby. I need to deal with 64 divided by 3. What am I going to do? I'm going to do long division. Now, just a note on division, I could write the problem like this, 64 with that division symbol. I could write 64 with a slash for the division symbol. Okay? Or I could write the division symbol as a horizontal slash. Each of these means 64 divided by 3. However, once we use the long division symbol, things kind of go backwards on us, because there I'm actually taking 3 into 64, and that's an easy one to mix up, because all of a sudden we put the numbers in a different order. Kids are used to reading left to right, they're used to reading top to bottom, all of a sudden, uh-oh, it's backwards. And that's going to cause confusion early and later. So usually I kind of separate these and say, hey, these are our division symbols. This symbol right here, we can either call it the long division symbol, it's long division, or we could call it the goes into symbol. So we want to figure out how many times does 3 go into 64. Now, long division, by the way, is an algorithm. An algorithm is a process. It's a series of steps that you follow. So, how many times does 3 go into 64? What do I do here?
So every times 3 goes into 6?
That's 6 right there?
Yeah.
Okay. Isn't that a 60?
Well, yeah.
Okay, we'll just call it 6 for now.
Yeah.
We'll break it down later. Yeah, so we ignore the 4 for a minute and say, how many times does 3 go into 6? Well, 2 times 3 is 6, so it would go twice. 2 times 3 is 6. So what is the long division algorithm? Basically, step 1 is you make a guess based on the first numbers you see. Step 2, you then multiply based on that guess. So I did my multiplication. What's the next step?
Bring down 4.
Why?
I don't know.
What happened to the 6s?
What
do I do with those 6s?
Oh, you have to subtract.
I have to subtract next, yeah. So the third step is subtract. There you go. Subtract. So I can go, all right, there, oh, it's 0, bring down the 4. And most kids at first, they'll write that 0, then they'll bring down the 4. And then they can come on to that. The fourth step is to bring down the next digit. Oops. Bring digit down. Would be the next step. And then we do it again. Okay, does 3 go into 0? Well, no times. Let's move on to the 4. 3 goes into 4 once. 1 times 3 is 3. Subtract, and I get a 1. And so then I have my quotient up here. we go, and the remainder down here. Now, we've all learned you could take this farther if you wished with decimals, but when kids first start doing long division, they have not gotten in touch with decimals yet. So that's the long division algorithm. So for that extension there, all I would like from you, I don't need you to do every single one of these, but I would just like you to explain a method for coming up with the quotient and the whole number remaining. Whether it's like Nikki's method or whether it's something like the long division method, but just write something down and then demonstrate it with one of these examples. Okay. So write down what your method is, either what buttons you would push on the calculator, kind of like we did a minute ago, and just show that it works for one of these problems. Okay, so I'm going to let you finish that later. Since we're on the subject of algorithms, I just want to mention a couple of algorithms related to the long division algorithm. So let's pick on this problem since we already know the answer. And we're considering 3 goes into 64. So when you first teach it, if you just start teaching it straight away without any prep for it, it's kind of weird calling that a 6 and ignoring the 4. And kids will do whatever you tell them, right? You're the teacher, you're in charge. No big deal. But you could do it thinking about place value. And so we could say, well, let's just focus on the 60 for a minute, right? And all the kids will know, yeah, that 6 means 60. How many 3s are there in 60? And you can start guessing at it. Are there 10 of them in there? And some kids go, yeah, there's 10 of them in there. So you could make a note over here on the side. I could grab 10 3s. What does 10 3s come out to? 30. So let's take 10 3s out of there. That leaves us 34. Can I take some more 3s out? And what do you think some kids will probably say? Do another 10, right? There's still 10, so somebody's going, yeah, let's do another 10. And so there's another 30 to come out. And there's 4 left. Oh, I can't take 10 out anymore. How many can I take, do you think? Right, somebody might say 2, and then say, well, what's 2 3s? And they would go 6. Oh, yeah, right, I can't do that many. But I could do 1 more. And so then I could write my 3 down, subtract. And so what we found is, altogether, we found 21 3s in there with 1 left over, 1 remaining. And that's a process that we could reuse, couldn't we? Okay. Now, for some numbers, if that was like 3,000 something, I would go with more than 10 at a time. But we probably wouldn't use numbers that big when we're teaching this anyway. But this system right here is called the scaffolding algorithm. Or sometimes it's called the groups. Let's see. There's a better name for it. Wait a minute. I just went blank. It is repeated subtraction. No, that's not it. Grouped repeated subtraction. There we go. This is called grouped repeated subtraction. And it's really a lot like long division, because long division involves guessing. This involves guessing too. This guessing is a little rougher, but that's okay. When we're first learning, it's okay to do things a little rougher and then fine-tune it from there. Another way to approach this, kind of similar to take the group repeated subtraction one more level, 3 goes into 64, is again, keeping track of that place value. So we do it again and we say, all right, we took more than 10 3s out of 64, didn't we? Okay. And just focus on the 60 for a moment. So we're just focused right there. How many more than 10 did we get? Well, didn't we get 20 out of there if we're just focused on the 10 spot? So then what I could do is just hold on to my place value and say, yeah, there's definitely 20 3s in there for sure. 20 times 3 gives me 60. Subtract and I get my 4. how many are left? And we go, well, there's one left. So then we just write the one up above like that. -3, and 1 is the answer. And so combined up here, I see my answer of 21 threes. And this method where I write them up above, this is called the scaffolding or scaffolding algorithm. So the most basic way to think about it is division often means repeated subtraction. You could just subtract 1 3 at a time and keep counting. Okay? I remember doing that as a kid because I was panicked and I couldn't remember what times what was what, but I could subtract all day long. For this problem, I got a whole bunch of subtractions to do, right? 21 of them if I did it that way. Here we can group them by tens, because 10's an easy number to multiply by. Here we're collapsing that a little bit. So there's kind of a progression. Just repeatedly subtract in groups, tighten those groups up a little more in the scaffolding, and then long division would be the next evolution of this. Now, do you think everybody in the world uses long division? Many countries use what's called short division. Let's take a quick look at that. With 3 into 64. So the way short division works, it works just like long division, but you write almost nothing down. That's the shortness to it. So starting kind of like before, I would say, well, 3 goes into 6 how many times? 2, yeah, and 2 times 3 is 6. 6 minus 6 is 0. And so then I just make a little note of the remainder right there. So I have to do the multiplication and the subtraction in my head. As I do that, I put the 2 up there. Now here I can see I just have nothing left over, but I have the 4 there. And so 3 goes into 4 once. 1 times 3 is 3. 4 minus 3 is 1. And so the remainder just goes right there. And so in a lot of South American countries, this is taught more commonly than long division. We'll try it for a bigger example. Let's suppose we're going to take 3 into 2,251. So we would say, well, does 3 go into 2? No. So let me say, does 3 go into 22? 7 times? 7 times 3 is 21. 22 minus 21 is a remainder of 1. And so I just write the remainder right there. Then I ask again, okay, does 3 go into 15? Yep, 5 times. 5 times 3 is 15, so there's no remainder. How many times does 3 go into 1? 0 times, which is significant because I have a place to put up there. And then is there a remainder here? A remainder of 1. So we think it's 750 times the remainder of 1. So that's short division. And there's a few other variations, but they're all pretty darn similar. They all involve subtraction. They all involve guessing with multiplication. There's no way around that with the division stuff. All right, and some of these algorithms are listed in the algorithm document I posted on the website, so be sure to take a look at that part if you haven't yet. All right, let's back up and talk about division models. We've covered a couple. And then we'll work some more activities. So the first model for division that we considered, the most common one, is the set model. That's the one I called the groups in model. So example of that, 12 divided by 3 means how many groups of 3 are in 12. And that was like my enchilada lunchbox example. The other version of the set model is called the partition model. Doesn't really have an alternate name. But in this case, 12 divided by 3 means split 12 into 3 groups. How many are in each group? Different question, different organization. Next model is just the idea of repeated subtraction. Divided by 3. How many times can we subtract 3 from 12? Oops. To get close to 0. Sometimes we get to hit 0, but sometimes there's a remainder. We can't quite get there. As close as we can. So that's repeated subtraction. Fourth model has a couple of different names. It's called the missing factor model. Or the what do I multiply by model. So for this one here, we'd say 12 divided by 3 equals what? And then I usually use a box or something, a placeholder for the what. The translation of that comes from reading it backwards. So this means the same thing as what times 3 equals 12. And you can either think about it as, you're trying to subtract to get there, you're trying to use a set partition. So you can kind of rely on the other models, but mostly this relies on knowing multiplication facts. And sort of think, oh yeah, 3s, let's see, 3, 6, 9, 12. 4 times 3 is 12. So we have to come up with the answer by knowing something about multiplication. So those are the main models for division. So remember, models, why is the answer 4? Show me. Algorithms, how do I figure out division for big numbers? I don't want a picture, I just need to know how to get the job done. Our general model there is we just do long division. I think short division is pretty cool. The scaffolding model is pretty cool. Worst case scenario is we just keep subtracting 3 over and over and over again until we can't subtract anymore. So that's one of the few cases where the model can also be an algorithm. We just keep doing it. Not ideal, but it works. All right, let's see. What else do we need to do today? This video is getting long. I'm going to stop it. Maybe make a new one.